Good afternoon, everyone. Welcome to our Trust AI seminar. It's my pleasure to introduce our speaker today, Dr. Yuan. He's an associate professor and Collins Aerospace professor in the School of Computing. His research spans security, privacy, and trustworthy machine learning with a focus on areas such as differential privacy, secure computation, applied cryptography, adversarial attacks, and provable defenses in machine learning, computer vision, large language models, and cyber-physical systems. His research works are typically published in top-tier conferences in security and data science, as well as in top interdisciplinary journals. He is a recipient of the NSF Career Award, Cisco Research Award. He also recently got the CCS Distinguished Paper Award, and also he received the finalist of the Meta Research Award. So today he will be talking about certifying trustworthy machine learning from defenses to attacks. And let's welcome our speaker.
Thank you for the introduction. It's my great pleasure to give this exciting talk here, to introduce our work on certification. So in the context of trustworthy machine learning. So we are focused on certification. Of course, I will talk about why we need a certification. So and from defense to attacks, we both can have certification. I think based on previous talks in this series, maybe you have already learned adversarial attacks and defenses. So about AI security, machine learning models, we need to care the robustness of the model. We also from both attacks and defenses. So the attacks we can disclose the vulnerability of the model. From defense we can make safeguard the model. So since the study of machine learning security in the past decade, at least attacks and defenses are proposed all the time against each other. So it's kind of a rally between at least two parties. They want to I break your system, your model, then you fix the model. Next time I break it again, you fix it again. So there will be endless. So so you will see the trustworthy machine learning can make this kind of attack defense entities. So however, if we can provide a certification in trustworthy machine learning, we can end this game. So because certification can provide us provable security for defense. Of course, we recently proposed a provable a successful attack. So since this year, I will introduce that later. So but mostly focusing on provable defense at this time. And the provable defense normally is we also call it as a certified defense. Certified defense. So that's why certification happens. And then certified defense normally we do guarantee also find out the condition for machine learning models that can make all the defense successful with 100% guarantee. So that's why we call it a certification. So but normally it gives us a kind of condition. We also need to derive such kind of condition. So for example, randomized smoothing is a very typical technique for ensuring certified robustness for classifiers, for example. Then for example, while training a classifier, then all the training data can be injected with noise. And when you infer the test data sample, the noise can be also injected to then a kind of guarantee can be derived based on LP norm the protection. So for example, since 2019, the work in ICML proposed the first randomized smoothing based technique for by injecting Gaussian noise to the training data as well as the test data sample to guarantee L2 norm protection. So it means any perturbation, they can derive a kind of certified radius as an LP as a space in LP norm. So if the perturbation is within the space, then attack won't happen. So outside the space, lens can still be effective against the attack. So however, there is no guarantee. So but the condition can be divided. So this is called as randomized smoothing. So and the conditions are here. So in this work, we first start to learn how this kind of randomized smoothing technique be used in models like other than traditional vision models. So like in text models. So like this work was recently presented in S&P. So, and then we move on to like a certification for text, like in the second half of this talk. So for text models, it's very different from like a vision model. So the noise, for example, Gaussian noise or even other different kind of noise they inject to the model, like to the data itself, may not work in very well in like a text model, because like there are some differences. Of course, let me first introduce a very simple, typical like a text language model for sentiment analysis. For example, very simple. Standard text given, like we use a model to classify the sentiments, like positive, negative, very simple, right? So, and then like there are multiple different kinds of perturbation can happen to text data. So for example, for images, for videos, like our perturbation is mostly focusing on like the pixels. Then we just perturb the pixels, the values. And then, however, for text, that can be very diverse. Like that can be, for example, like the first kind of group of text like result from like a synonym substitution. So we change like a word like with like a close like a lot of word, but that can change like the result of the model, like to fold the model to get a different result. And in practice, there are four basic operations which are considered as possible adversarial text for text data. So for example, there can beyond synonym like a substitution, we can also do reorder like the words, we can or tokens, or we can insert a new word or delete the existing word. Those all these can result in like a different result, like the prediction outcome for the language model. So this is not just the noise of the perturbation inject to the image data anymore. So this poses us more challenges. And so the motivation for this work, like we try to provide a kind of generalized framework for certified defense for language models. Actually, there are some works proposed earlier, but there are many limitations because there's no generalized standard for in this domain before. So for example, like some models they can do like provide a kind of guarantee as like a L0 norm, like for example, the number of like words which are like substituted by synonyms that can be provided as a condition. So but that's not that can some but that's only limited to one type of adversarial operation. And some works they have assumption on specific model structures. They cannot make it like the defense universal. And so that's why and some defenses they cannot provide practical like a result for the guarantee. So for example, we can divide a kind of like condition as our condition to trigger like a defense with 100% guarantee. However, like we need to also make this condition like practical in our applications to, for example, have like a real world implication about how this like attack happen and what is the guarantee over there. So there's no practical guarantee over there. So in this work, we try to provide this kind of generalized framework for language models. So, and of course, we provide a much better like accuracy for the certification. So even if we know like a certification is 100% guarantee, so but the radius also matters. That gives us different like evaluation metrics over there. So, and then I go back again to like technical challenges about language models. So for example, like the data is different from images. Then we like it's unstructured. Like especially when you insert a new word, like the word is from like a huge space, like we don't know, and there are many different places we can insert a word. So like that gives us a lot of challenges, and also the operations I just mentioned, there will be 4 different kind of operations that can be used maliciously for the attack, and they can be combined like as a subset or like arbitrarily. Then it gives us more challenges for the defense. And also traditional measurement about the defense. For example, we use like a certified radius as like an L2 norm or LP norm board to measure the space for certified guarantee. May not work well here because like the distance measured on text is very different from like the distance measured from image data. So like image data, we can measure the distance. We can measure we can provide a guarantee within like the distance within the board. Like then, so but here if, for example, if we insert a word, we definitely cannot measure like a distance between the tokens. That can result in huge distance. So but semantically it may not be that huge. So there will be new challenges here. So that motivate us to provide different kind of methods for randomized smoothing to randomize our data for training the model, to fine tuning the model, while inferring the test data sample for text for language models. So then we focus on guarantee in the embedding layer. So for the language model, and introduce a lot of embedding layer and provide a guarantee over there to address the first challenge. And for second one, we need to generalize the randomization from traditional Gaussian noise or even Laplace noise, for different kind of guarantee, to more flexible a set of randomization mechanisms to provide us better performance in different applications against a different kind of attacks. And regarding a huge absolute attack distance, it's hard to measure. So then we still then we need to find out a good measure for this kind of guarantee. So that's why we look into the embedding space to get to decompose the attack into a combination of permutation and the embedding transformation, and then provide a guarantee for each of them and altogether. So the framework will be like this. Then we disentangle general textual adversarial attacks that can be synonym substitution, can be insertion, deletion of existing words, can be reordering existing words in the sequence of them. So into a universal framework. And then all these kind of attacks can be represented as two operations, as a permutation of the tokens, as well as embedding transformation. For the corresponding embedding, then we can apply kind of transformation over there. We can randomize the embedding over there. So we randomize this and provide a guarantee also as a kind of radius, but the radius here will be LP long, so we do not fix that to L2 long. So that gives us more flexibility to create a guarantee. So for these four, we can four kind of tags, and then we can try to get the permutation operation and also embedding operation applied to the embedding space. And finally, we provide a guarantee for four different kind of operations. For example, a substitution, but for substitution, we only need to provide one kind of guarantee because we don't change the order of those kind of words or even tokens. But for a substitution, for reordering, we also need to provide one type of guarantee because we just reorder the tokens. We don't change the embedding or the words over there. And but for insertion and deletion, operation wise is very straightforward. However, the guarantee wise is not very easy because that expands our sentence, also shrink our sentence by deleting existing word. That may pose more challenges. And then we need to provide two kind of guarantee in terms of both permutation and the embedding transformation. So let's formulate a problem. And then the guarantee, of course, we have done theoretical studies for this kind of guarantee. I'm gonna skip that later. So, but again, we summarize this kind of framework to provide a guarantee for the original. When we train a model or fine tune, even we fine tune a model, for large language model right now, we can do that for the filters, for example, the LLM filters. We can do that for fine tune the data. We can also work on the data instead of retraining the model because certified robustness may need to retrain the model in general. This may pose additional challenges for large language models. So, but now I still go through the general framework right here. So the basic model, AI model, then different attacks we have identified and retrain the model or fine tune that with to add corresponding noise, of course, we need to study the noise to find a good noise for different kind of operations against different attacks, and then to make the model robust against the adversarial perturbations. So then finally, we need to do like a verify the model and also verify the robustness, also divide the condition for certified defense. So that's the general framework for this kind of certified robustness. And we also provide different kind of like theories against the different operations. And we use different randomization. For example, a synonym substitution attack, like we identified that like a staircase randomization can be the best noise. We can say as like this kind of noise applied to data. Like so, for example, every word like we can randomize the word. For example, like randomize the word as like by constructing a kind of staircase shape like a PDF or like a probability density function. So for the center will be the current word, and then like the symmetrically like the closed word synonyms can be used, and then randomly choose like the synonyms to replace the current one as a kind of randomization, which can provide a guarantee like for the robustness. So like against the first type of attack. So and of course like closer one, the probability will be higher. So this makes like it's like a staircase shape like a PDF. So like the further ones will be like the probability will be lower. So like it will be like a staircase. That's why we call this as staircase shape like a randomization. So for permutation, like we observe like the permutation tag like that can be similar to kind of like a uniformly permuted like tags or tokens. Like so that's why we use uniform based perturbation permutation for randomizing like the order reordering like while training or fine-tuning data. So and then for insertion we use Gaussian based noise. For deletion we use Bernoulli based randomization. So that means like those kind of tags used for training or fine-tuning will be randomized, which can provide us guarantee. So and the guarantee will be provided in the embedding space as I just introduced on the previous page. And we have many like results to show like, but I want to go to the details of like the result, but I want to explain okay how it performs in practice. So for example, like for synonym substitution, our text CIS, our framework outperformed the existing work for safer, also a lot of one CISS. These two were two existing certified defense against the synonym substitution, and these two works one for example safer provides a kind of guarantee as like if the number of words substituted less than a threshold, then attack won't happen. So it will fail. So like that's a guarantee for like at the word level. So then, but we provide like a guarantee in the embedding level that which can outperform them like with a much higher accuracy for our we have larger radius. Like for example, like we divide like guarantee condition over the space is larger, that can be more resilient to higher perturbation in practice. And also our work provides the first kind of certified guarantee against the word reordering, insertion and deletion. So, but we still need to evaluate the performance because randomized smoothing provides us like a certified guarantee, but there's a downside. So because why is there a downside? If I inject noise to the training, what is the problem? That's the question here. The model is like the model is not as original as before. So that is resilient to attacks. However, if the data is not attacked, like the data is not perturbed, then like the accuracy might be lower a little bit. So that's why we need to make it as close as possible to like the clean vanilla model. So that's a very big challenge for this kind of guarantee because it's a trade-off. Normally for security and privacy research, there's a trade-off between like different like metrics. But here, now like but here like our clean vanilla accuracy here is pretty high compared to like existing works. And also some other words like about substitution and reordering, like there will be some performance. We provide a guarantee like within a number of like so. But we also need to remember like on the first page, we claim like practical in the big table over there. Practical means like we can translate our guarantee in the embedded space to practical like practical perturbation like implication. So for example, for synonym substitution, we use like staircase randomization for certified robustness. It can make it, for example, like if I give a guarantee as a radius as 200 for a sentence with a length of 50, that implies that each word can be substituted with these four closest synonyms. Like so, like that means each word can be substituted. That's a very strong guarantee. So that means like if this substitution happens to each word, like as long as they are not like exceeding the number of like substitutions is no greater than 4, then attack won't happen. So like that's a practical like implication of like this guarantee. And for reordering, for example, like we transform like the guarantee from the embedding space to like a practice as like the sum of all words positions changes will be less than 100. So like for every word, like we can have a marker like position. For reordering, like we can measure like the reordering like the position distance, right? So like the changes, then like the total sum can be bounded based on our guarantee. So as long as they are within a guarantee, attack won't happen. So that is some, and also for insertion based on Gaussian noise, we can provide like so for example top 5 top 50 for example closes embedded like to insert words randomly. So but of course like we cannot provide a kind of guarantee to any kind of word like in our whole space, right? So but we provide a guarantee against like insertion based on the random words with for example out of like top 50 like out of the words with top 50 closest embeddings. So like that, the guarantee is pretty good like as well. Okay, so question. Yeah, this is a good question. So so like different attacks. So here we break down like a defense to different operations. So we provide a guarantee. So if we are together, we can also analyze like this kind of operations. And of course, like analyze these operations and not also derive like the title bound like based on these different operations. And some operations can be merged together. So that can be so for example like deletion and insertion can the combo of these two can represent any kind of attack, right? So like it's worthwhile like to study this like to make like different combos for different attacks here. But we break down to like the building blocks for the defense right here. Yeah, good question. Yeah. Mm-hmm. So and deletion, like we can, for example, radius 2 means like up to 2 words can be deleted while ensuring a certified guarantee. Like given like the radius 2, for example, like like that means any 2 words can be deleted without changing like the final inference result. So this is still a kind of strong guarantee. So and like also a worst case guarantee for certified robustness. Okay. Okay. Any questions so far? Any other question? Go ahead. Any pattern like inserting like the data or? Oh, that's a good question. Like, so this will be a kind of like a personalized like defense. So here we provide a kind of general worst case defense. So like for if we check into like a specific like perturbations to for example different words, different tokens, like they might be more vulnerable, then the performance can be even better. Yeah. So good question. Yeah. Okay. So okay, so then now we'll move to the next work on like a certifiable black box attack. So And this was recently presented like at the CCS. Mm, I think like this work is like focusing more on attack. However, most existing attacks, especially in black box setting, they are focusing on like either query based attacks when I'm query over the black box like target model, and or like using surrogate models to craft like an adversary example to make the like prediction like inaccurate. So and we also study this kind of attack in black box setting, and this is a traditional problem as black box attack, but we study a kind of new perspective to focus on like provide a guarantee for the attack. So and in this scenario, for example, it will be either hard label like based on black box attack or like a prediction score that can hard label here means like we focus on changing the prediction label like of the test data sample. And also like a prediction score means like we can change the scores of the prediction that will be more follow-up learning like or like inference results based on the scores. So there are two types. We compare our work focus more on hard label like a black box attack. However, we also benchmark with like the other category in our experiments, and this work like so so before getting into the details of this attack, I would like to introduce, of course, again, motivation, why we need this kind of certified guarantee, and why, what is the benefit of this kind of new attack? Because when we study security and privacy, like we propose new works on attacks, our ultimate goal is to defend the system, and so that's why we disclose like the vulnerability and then find out good better defense against new attack. So right here, so for the black box attack, for example, query-based attack, so there will be initial adversary example, for example, then like try to refine adversary example. Like, there are two goals. One is like to make the test data sample like cross the boundary of the classification. For example, from like from the original one to the adversarial one, and then, but of course, they need to make like the perturbation insert to the adversary example minimum. So that's why they need to sometimes step back to make it like a more like a human imperceptible. So that's why there's a process here. Maybe after the second stage, like the label has been changed. However, they still need to shift back to make it more like difficult to detect this kind of attack. So that's the standard one. So, however, recently, like this kind of attack have been fully studied actually for defense. There are some state-of-art defenses proposed for against this kind of black box attacks. Very traditional problem, classic problem. And there are two types of defense methods. One is called as like a detection. So they try to identify this kind of perturbation injected to like the data sample, and so there's the state-of-art defense method, which is called like a black light, try to detect all those kind of like behavior, like by tracking these kind of queries. Like the attackers, they try to query over the target model and using like the input. So the result can be tracked by the defender. So then they can use this because like while they are refining the quality of the data sample, like these queries are very close to like the results are very close to each other because they are iteratively updating like the adversary example. So that gives us a trace of these kind of query results. So blacklight, the idea of blacklight is like to try to trace this kind of close queries and then identify adversary examples from there in the black box setting. So this is a typical it can achieve very high performance for defense, 100%, like almost 100% accuracy for detection. So another type of defense is called as interruption. So because in general attack happens, for example, starting from X, like in the original class, they try to query and then try to move like the adversary example across the boundary to like an adversarial class. And then, so based on this, the first one can be detected. The second one, if the defender, they try to inject noise, add some noise into, for example, the input of the query or the output of the query. So two type of like a interruption. So that can make this kind of query results or query itself like a fluctuating. Then like attackers cannot easily trace this sequence of data samples to find out the best adversary example. So that you can see like right here. So like the attack will fail like in most cases, because that's an effect. These two types of like state-of-the-art defense methods have been well studied. So, and our job is to find out like the weakness of these two different kind of like defense methods. So you can find out like, so far they have very good performance. However, if we can add some randomization to like to the attack, to add some randomization to attack, then like it can easily break the defense. So for example, so if I go back to here, if we randomize something here, it will be difficult to trace. And if we randomize here, of course, the defense is randomized here. So, but we still randomize it, but we can get some interesting results over there. So that's why we motivate our work to attack from like our work on defense. As for example, as randomized smoothing I just mentioned, like for certified robustness, like that will be injecting noise to training data for making the model more robust. So that will be in a true data, like original data, to make it more robust within, make it like the results staying within like the original class all the time. So but here, like let's attack, that makes, okay, the attack should make an adversary example across the boundary to an adversarial class, right? And we try to randomize it and make this kind of guarantee to the adversary example always stays within like the class of like an adversarial class. So here, so like this is the first work to make some randomization to the attack here. And I ask another question here: why we need like a guarantee? Because like a certification, what means guarantee? Why we need, so for example, the guarantee here will be we provide like a 95% of confidence to the attack successful rate. Why we need a guarantee here? So we can break the defense. Why we need a guarantee? Because it's question. Yeah, of course, definitely. That's like, yeah, we need to, if we know about like the attack performance, let's of course the quality guarantee, right? So that's a good point. So in practice, we have more motivation. For example, like if we randomize our attack, like randomization means what? Means like a continuous like distribution. For example, that makes like any kind of performance can happen, even if there's a slim chance for like some outcomes, right? So that can make like the attack or perturbation unpredictable, or like and if that unpredictable, like then without guarantee, it will be out of like suppose we're attacker, it will be like a message to like the attackers as well. So if we can provide a guarantee, at least there's a confidence for like for randomization that it can make like make the attackers feel more comfortable, right? So at least like in a simple word, right? So but in practice, there are some interesting findings too over there. So that's why we provide a kind of new paradigm of like a black box attacks as a certifiable attack. So we certify attack and provide like a lower bound for the guarantee and randomize like an adversary example. So randomized adversary example means like we cannot guarantee always like 100% of accuracy over there. So however, we can lower bound that to 98, 99%, for example, 95%. So we can set up a kind of like a guarantee for as a parameters for the attack. So we focus on like a query-based attack. So that's why here we can query like a randomized query over in a batch. So then this kind of state-of-the-art defense may not work in practice. So But I still want to compare these two kind of attacks because like motivation is very important again. So because like this is a new type of attack. So and we need to like describe. For example, like because it's stronger, we can claim this attack can break like existing defense, so it's stronger, right? So we consider like an existing black box based attack will be like an empirical attack. Empirical attack, so they query over like a different like a target model to get different results. Finally, you get like a final adversary example, and so based on the black light, they get this kind of detection easily. And also they can inject noise to like a defense to make these kind of queries obfuscated to defend against attacks. And in our case, you will find out like it's randomized. It will be randomized, so the query will be also randomized. Then like so we are exploring a kind of space like in over the query over like the class the label in the adversarial class like in a bigger space. So it will be difficult to track by the black light defense. So because they are tracing this kind of perturbation based on distance. So they make it like okay, those queries are very close to each other, but in our case, the queries are very far from each other. So like a black light cannot work here. So and similarly, we have like a randomization in our attack together with the randomization in the defense that makes a bigger randomization. So that still makes like our attack happen. Like so even if it's in a bigger randomization here, mixed randomization. So that can break like the state of art defense in this way. So and there are some other differences. For example, our goal for studying attacks will be focusing on identifying like vulnerabilities of the model. So like these attacks, they identify these kind of adversary examples as point by point, right? So like one, but we can disclose like a whole space. We can disclose like this kind of space. There will be even more space of like a vulnerability, like vulnerabilities in practice. So and of course there's a difference. Like right here, like everything like queries over the model that gives us 100% guarantee like finally because they tried 1,000 times and finally getting like a 100% guarantee. So but it's unpredictable. That can be 10,000 times or 1,000,000 times. So like there's no guarantee over there. So but right here we provide a kind of lower bound, for example, 95%, 98%, like so on and forth. And then but we can keep querying. So then eventually to get like 100% accuracy very quickly, like in 1 or 2 trials, that will be the final result. Yeah. And also another benefit of this kind of certified attack is that we don't need to verify, like we can get a guarantee without verifying like our adversary example. So before sending out this adversary example to the target model for query, we already know like how much guarantee, how much percent, lower bounded percent of attack successful rate can happen. So that's a like at least can build confidence for the attacker, right? So like from this perspective, this is supposed as a guarantee. Okay, so there are some benefits by considering by comparing these two types of attacks. And then we have like some math to build up this attack. Of course, I will skip the details. And so to provide this kind of guarantee based on queries, we still query. So but our query will be in batch, like and in parallel, like we have multiple queries over there. And we can have derive some hypothesis, use hypothesis testing to get like a lower bound. And we in the attack framework, we similarly we also start from one like the input X here, like which is in the original class, and try to shift to like the adversarial class. And of course, we can first localize different like initialize adversary example, and we need to shift it back to like the boundary to make it more perturbation as minimum as possible, which can be like less detectable, so or perceptible. So like we have this kind of localization with different methods, and then finally goes back to like a boundary of like those two classes. The original class, the beeline class, also the adversary class, make it staying on the boundary. So and so on and forth. Finally, we sample like an adversary, sample the adversary examples. Then that can give us more. Like we can, for example, we can produce like thousands of adversary examples in a batch. So which are much more than like one single like adversary example in the traditional text. So that is like and we have guarantee algorithms to you can see like how in the paper we showed how to shift it back to like the along the boundaries of like the classification boundaries. So for adversarial classes and the original class, yeah. So on and forth. And we visualize some result here. So the clean input are given here as two examples, and then we try to initialize that in like suppose in this format it might be in falling into like an adversarial class. Okay, so and then we go to like the so like go to like the like this and going back and shift that back to like the boundary. So you can see like the images are very similar to like the original images, but like the models they are fooled to get like the wrong prediction. So but you can see like the perturbation is very minimal here. Yeah. Okay, so that's some example here, and we also validated that based on like a different adversarial lower bounds and actual bound, and we find out in practice our worst case guarantee for the attack is always like lower than the actual performance. So like in practice that can be even better. So more adversarial like adversarial examples are generated in than expected like in practice. Also, we also benchmark SOTA attacks against the SOTA defense. You'll find it here is very funny here. So and but we have done a lot of experiments in this work. We open source that all the code like for based on 4 data sets, CIFAR 10, 100 ImageNet, also like a speech regulation data. So we work on multiple domains, like the attack on multiple domains as well. So multiple models, 4 state-of-art defenses, we try to break them, and 16 baseline black box attacks. So all of them. So when you open like the page of our like repository, you will find a lot of results, a lot of code over there, and substantial experiments on 3 image data sets and 1 speech data set and 4 models, 4 defense, 16 attacks will be 754 sets of experiments. So the paper is very long, like 24 pages. So and like a lot of and also result against adaptive defense, adapt like ablation study to give us more explainability on like the results on attack and so like so on forth. So you're very welcome to check like the detailed results over there. And we have all these like and including our baselines are also open source, like, yeah, in practice. And of course, like time is limited. I cannot present everything. So like all the results are in the paper, like a full version, like a lot of. Even the CCS version is like a lot of full. Okay, so and some attack performance you can find out here. Like at the very beginning, we check like list all our baselines different, and we have 2 methods for our certifiable attack, and as the perturbation size grows, then like we require some perturbation size to make like a attack successful rate high right here, and some attacks works very well. You can see here there's no difference. So this is a result without difference. So you can see many black box attacks they can achieve nearly 100% of like a successful rate. So similarly, we are doing like close to 100 as well. So some attacks are not that good, so but we still involve that into the comparison. But once we equip like the defense with like black light, for example, so the metric here has been changed to detection rate. It's detection rate. It's not an attack successful rate anymore. So all of them are close to 100% of detection rate. So that can be easily like detected by black light. So blacklight is the state of art for the defense by tracking the queries. So it's difficult to detect hours. It's close to zero for under on randomization-based defense. They can do either pre-processing or post-processing. Pre-processing means like they pre-process like the input data, like and then for each query. So like you can find out our attack here, like a performance drop is like close to zero, so still close to 100% of like attack performance. However, other attacks you can see, most of them have a kind of some drop to the performance, and some might be very high. So we achieve the highest attack performance against the randomization-based defense as well for both. So for the second one is also interesting. It's like a post-processing based method. You can find out like for the hard label based attack, black box attack, the performance is like is pretty. The performance for defense is pretty good. So like, however, for the score, basically like black box attack, like the defense, the drop is not very, very significant. Like, but we have comparable performance, like which cannot be easily like mitigated based on the randomization based defense post processing, like processing the query results. Okay, so like some interesting results like showing here, and also against the adversarial training, against the certified attack, against the certified defense, how it works. So like we have some results in the paper. Due to time limit, I cannot show everything here. So but you can take a look. And against the adversarial training, our performance is also good. We don't need many queries to achieve a good performance for attack. Mm-hmm. So any questions so far for the second work? Mm-hmm.
For white box, we struggle to defend against effectively. Even like say training, that's probably the best. But for black box, maybe there's a way to defend it in black light test. It's like pretty successful. So people were starting to think about like maybe we can ensure the black box knowledge to the attacker, then there's a chance for us to achieve a good defense. Because this work is showing that maybe by compromising certain amount of queries, because I believe compared to the without defense query, the query number is going to be increased because of randomization. But this eventually says that black box defense or white box defense, I guess if there's like no secret black box defense that can work for black box setting only, we should, in the event, like, still build a robust white box model that eventually can work well under black box setting.
So white box attack or white box defense? Like
so, the simplified statement is that it seems that the community might have some impression that maybe we should design some customized black box defenses to defend against black box better. So your attack is kind of showing that actually it probably doesn't work in this way. You may still have to resort back to design like robust white box defenses so that it can defend against both the white box and black box.
That's a good point. Like for white box defense, like yes, it's like interesting to like to have this because like white box defense is assumed to be the strongest defense. Like we also like have some results to apply this attack to white box attack against the white box defense. Like so because like because this all performance actually can support both. So but black. So like for the black box defense one, like so far like SOTA is over the like very effective as you just mentioned, right? So like so that's why we're highlighting this on this work to as a significance for this attack. But against like white box defense is also working and also interesting to build up the knowledge because eventually we need to make the systems more robust. Then like by identifying these kind of vulnerabilities, then definitely it's a good like a strategy or like interesting to merge these two together, like in the final defense. What about this defense? Yeah, good question. Thank you. Any other question? Okay, so then I will move to the third part, like our other like research works recently published, like related to trustworthy machine learning. Hopefully, we can like have some discussions about those topics. So like first I will overview some like certification-based works for trustworthy machine learning. So we our certification can happen not only for models, like for classification inferences, that can be also working for like for example like to ensure certifiable robust watermarking. So for example, the backdoor-based watermarking can work like in practice to trace like to verify the ownership of like the models, and then but attackers they try to remove the watermarks from the model, like they can possess some and watermark the data samples to train like the model and to replace, for example, like the models layer by layer, like by using unwatermarked parameters, and then we develop a kind of certified defense against like as a condition as the number of layers which is have been changed less than a threshold, then like the watermark cannot be removed like by the attack. So also we also propose like the backdoor like certified defense against the backdoor like attacks. Also, we also work on like certification for like from more math perspective. So on like approximating like the boundaries like for the guarantee. Also like by using like also investigate like the anisotropic noise, means like so far all noise is like isotropic, means like every the noise the distribution itself is the same for all dimensions, but the performance can be further improved by making them like heterogeneous. But it's more challenging to find out like a condition, the boundaries in that case for certification. And we also try to extend the work to LLMs, like for defense, for example, filters, like of the to for more safe filters of like LLM to provide a guarantee over there. And some other attacks we also propose like on machine learning. Recently, we have like the backdoor attack for code generation models. And that's kind of a double backdoor, like a backdoor to the model first, and a backdoor which generate code, malicious code or vulnerable code, like which also includes like a backdoor in the software. So it can be considered as like a dual backdoor in this case. And we also try to make it more practical to attack like the video recognition system in real time, to inject the noise like in real time to learn like the kernel of the noise offline, and inject the noise online like in real time to change the perturbation, to change the prediction results for video recognition systems. Like for example, suppose there's like a anomaly detection for the behavior like explosion, for example, like in a gas station. So like the alert can be triggered like to a high score. However, after this kind of human imperceptible like noise injected to like the data, like they will be flattened to always like keep it quiet all the time. So like that's like a practical application of adversary example in video domains. And we also work on privacy. A lot of differential privacy works, also secure multi-party computation related works on making data private. And these are fundamental works for differential privacy. And we also moved that to machine learning privacy, like to develop the upper bound of the privacy leakage against a different kind of inference attacks. And also like for LLM, like when they use like agents, for example, like to when you send out like your task to the over LLM, your privacy might be leaked. Then how to protect like the entire procedures, like in such kind of interaction based on crypto systems over there. Okay, so thank you so much. Any questions?
So you mentioned a couple of different media, from text to image to video.
Yeah.
For different media, there are different kind of redundancies. So if it's the same type of, I guess I wanted to ask for the same strategy for text, which which media would be more difficult for giving you
The
harsh prompt for the
good question. It's a good question. So like the challenges are different in these domains. So like for example, in text, it's difficult to find out like a good measurement for like the guarantee. So that's why we look into the embedding space to get a guarantee over there and then convert it back to like the word space. And so like for videos, for example, like a computation cost or like even I think like because video, like compared to images, videos will be multiple frames and the perturbation size will be very big. So if you measure that in L2 norm or L infinity norm, of course, like we can get like the same bound like in all the dimensions. But L2, L1, we need to accumulate that in all the dimensions, and the video is more highly dimensional. So like whether such kind of like radius is effective in practice is very difficult to guarantee, like in video domain. So, for example, even if you get like a L2 long or like as like a 2, for example, for image it may work very well, but for video it will be almost nothing. So that's why in this work, in our SMP22 work, we evaluate like our perturbation, like this kind of real-time perturbation against the certified defense over there. Like the radius was very small, like in the video data, like because of high dimensionality. Yeah. So challenges are very different. So yeah, and but for fundamental challenge will be always finding a good strategy to randomize the data, and also deriving the theories to guarantee like the protection. And the third one is like to translate like the guarantee into practice. So there are multiple challenges in different domains. Yeah. Thank you. Good question.
Yeah, I'll ask one question. So the University of Chicago, they proposed a solution to protect the hardware from being damaged.
Yeah.
Also, we also have a similar. So I was wondering because other researchers argued that this defense can easily, they can use a single process method to break this. I was wondering whether it's possible to develop a certified approach to protect data, protect ownership.
Yeah, it's good question. Like
under this potential.
Yeah, I think there's a good potential over there. So, however, like we also need to evaluate like the cost, because here the cost will be like accuracy job to like against like the on like a clean data. So that really, yeah. So for 30, yeah, that's very true. Like I think that depends on how like the kind of certification guarantee can be derived over there. So if the performance drop is like okay, I think it's very doable. And also I find out in practice sometimes like a certified defense or even adversarial training can pose some downsides, like in some models, especially in like the like ownership protection model. I find out we find out the kind of problem is like which can reduce the performance for authentication. So like yeah, so that's also possible. Yeah. So yeah, but it's worthwhile to find a good trade-off between these two to eventually make it work. Yeah. Yeah, no problem. Thank you. Good question. Yeah.
Any more questions?
Sure.
So for the second part of saying that actually we would like regions of vulnerabilities instead of scattered points.
Yeah.
I was trying to understand the equation because of the randomization, like we can probabilistically can jump into like many for example, for the same initiator, for example.
Yeah.
That's the main.
Yeah, exactly. Yeah. But there's something we can discuss here is like because all these points are with 100% accuracy, like a guarantee, like by trying multiple times of like backdoor, like a black box setting. So, but in our case, we can guarantee like a lower bound, but not 100% here. However, like once you try multiple times, you can make this space to be 100%. So that can give us more like for example, give the model owners like more implication, like least boundary, least like a space of like inputs may have a problem in your model. Yeah, so this can give more knowledge to the defender. Yeah. Yeah. That's good.
Yeah, thank you.
Thank you.
Let's thank the speaker again.
Thank you so much. Thank you. Thank you so much. Appreciate it. Oh, thank you. Yeah. Thank you. Thank you. Thank you. Thank you so much. Thank you for coming. So, all good?
Yes.
Yeah.